Bonjour. Hello, everybody. Cherokee is the native language of the indigenous peoples of the southeastern woodlands near the Great Smoky Mountains in present-day North Carolina and Tennessee. Its writing system, seen here, consists of 85 characters, each representing not a letter, but a syllable. For example, here's how you'd write the language in its own script, ja-la-gi. Cherokee is among the most significant linguistic contributions from the American continent, and a profound aesthetic achievement in its own right. What's probably most remarkable is that it was created as recently as the 19th century, and by a single person, no less. His name was Sequoyah. He was born in Tuskegee around the time that America declared its independence. And in his 30s, Sequoyah worked as a silversmith, trading with European and American soldiers, and eventually fighting alongside them in the War of 1812, as many Cherokee did at the time. As the story goes, one day, Sequoyah was talking with some soldiers about an incident that happened involving the capture of a prisoner. The prisoner was found with a message, and having intercepted that message, the soldiers were able to learn about a planned attack by the enemy. Sequoyah had no formal schooling. Practically speaking, he was illiterate. So to him, the idea that someone, anybody, in fact, could get that much information from a piece of paper, what he called talking leaves, one might think it to be a kind of magic. Sequoyah would spend the next decade of his life trying to convince himself, his family, and his community that it wasn't magic, but instead was a tool that he could use to spread the language that he spoke and loved around the world. I love that story so much. My first encounter with Cherokee was right here in the Carnegie Museum of Art, the Hall of Architecture in Pittsburgh, Pennsylvania, my hometown. It was for a high school field trip. And looking up at the ceiling, there's this art installation against the skylights. You see the letter forms of the Cherokee writing system. And it's beautiful, and it's familiar, but also unfamiliar, and it's just something else. Some years later, I'd decided to drop out of the computer science department at Carnegie Mellon, just up the street from that museum, and instead studied linguistics. I wasn't calling it quits on computers by any means, but it was something that gave me a deep appreciation of text and language and rooted pretty much everything that followed in software. So today, it's my privilege. I'm so thrilled to share a little bit of my favorite subject with you all. I hope that you'll learn a few things that make you more, capable developer, of course, but what I really hope is that by the end of this, maybe you, like Sequoyah, can think that strings are a little less magical and are instead a practical tool that you can use yourself. I could ramble on about this endlessly, of course, but we have other talks to get to. So we have maybe 20 more minutes. Let's divide this up into 7 parts. Getting right started with a collection, strings as collections of Unicode characters. So fundamentally, all written languages attempt to solve the same problem, which is representing language separately from its essential spoken or signed utterance. And what's so fascinating about written language is that it represents a universal problem with thousands of solutions over thousands of years. Many languages independently arrive at the same patterns. Others are entirely unique and surprising. As a broad generalization, though, many writing systems begin as pictorial representations of objects in the world. And over time, they become more and more abstract to represent the sounds, and those sounds combine to form other words. And I mean, you can see this in the Western writing systems. What gave us Latin script, what we use in English and French? We went from a pictorial prototype of an ox to a Phoenician notation, a simplified way to write that and to draw that. And that became more and more abstract in the case of the Greek letter alpha, and then what we have in modern Latin capital letter A. As a fun aside, that word ox in Phoenician, it was used to mean leader. So if you ever wondered why A was the first letter of the alphabet, that's why, it was an ox. Another fun fact, if you ever wondered why it's called an alphabet, it's the first 2 letters of the Greek alphabet, alpha, beta. It's fun. By a similar process, Eastern writing systems also evolved from pictorial representations, but evolved through many more discrete steps. I think a lot of that has to do with the Chinese traditionally having a very strong record-keeping system. Their bureaucracy is fantastic, and you see that evolution over time. However, it's not a necessity that everything develops into an alphabet. They landed on an ideographic or logographic writing system in the end, very different than our alphabet. So for your consideration, let's talk about characters. We define a character as the fundamental, the atomic unit of a writing system. And we can categorize all writing systems that humans have come up with so far based on what that unit signifies. In the case of ideograms, those pictorial representations, each character is an idea, the actual object in the world. For logograms, each character is a word, which is separate from the object in the world. Alphabets say that one letter equals one sound, or a phoneme. Abjads say, okay, we're going to merge consonants and vowels, whereas abjads say, consonants, that's all we need, we can infer what the vowel is. And then there are syllabaries, where one character is one syllable, or a mora if you want to get technical, like the to in Tokyo is one syllable but two mora because it's held out. As software developers, we can immediately recognize that each solution has strengths and trade-offs, and it's just a wonderful thing to look at. I just love looking at all the different languages and all of the solutions that have come up, and here's a good overview of what we have in the world to give you a broader context. As far as the alphabets go, the number one is Latin, with over 6 billion users worldwide. But of course you have Cyrillic and Greek and Armenian, and my favorite, Korean Hangul. You have abjads. Those are basically Arabic and Persian, Hebrew, Semitic writing systems. You have abhagitas, which are largely used in the Indian subcontinent, with Devanagari script for Hindi. You have syllabaries like Japanese, both hiragana and katakana, as well as Cherokee, of course. We have logograms, both traditional and simplified Chinese letter forms. And we have ideograms. If you actually want to find pure ideographic writing representations, you get those with emoji. Also, any of the dingbat symbols that you still have. But the relationship between language and computers, it goes back, all the way to the very beginning. Traditionally, a byte was defined by the number of bits needed to represent a character on a particular machine, hence the char type in C. There's no such thing as plain text, though. That's a really important thing to remember. At no point can you, for instance, slice an Ethernet cord and have letters spill out. It's all numbers. It's all ones and zeros, pulses of light being mapped, these physical phenomenon being interpreted into an abstract representation of numbers. And that system by which you associate those numbers with characters, that's called a character encoding. The first standardized one was ASCII. I'm sure pretty much everybody in the room is familiar with ASCII, if not just by name. If you ever wanted to see that in its full glory, here you go. This is the ASCII encoding chart. And what that is just putting a number to a character. You'll notice the first top 2 rows, those are all control characters, the first 32. You also have delete at the end. So we have 95 printing characters. One of the nice features of this, notice that capital and lowercase letters at the bottom, they're only off by 1 bit. So in early hardware, you could do case-insensitive matching just by manipulating a single bit. So using ASCII, you can represent a string, like hello, by encoding each character using its equivalent ASCII code, followed by the null byte at the end to terminate the string. It's pretty easy. But not long after ASCII was standardized, other countries started to have some questions, like Danish is all like, where are my vowels? And Japanese is like, could I please have a yen key? So ASCII didn't provide these characters, and a number of national variants instead were created to fill that gap. And that's how we arrive at ISO IEC 646. That was in the early 60s. So same chart as before, but we have some blank spaces where each country could adopt its own national standard. So of course, US invented the ASCII standard, so it's pretty much unmodified. The Danes got their vowels with the slashes through them. The Japanese got their yen key. And actually, that causes, still to this day, a problem. For instance, if you're on Windows, the backslash has been replaced by the yen key, so you might have this showing up occasionally. I myself use a Japanese keyboard, and it's still an issue. If you were to represent the current state of affairs in the early 60s with a piece of art, it would look something like this. Jackson Pollock is a perfect representation. It's beautiful, it's functional, but it's a total mess. It's chaos. So, as a way to rectify this, in the late 80s, ISO IEC 8859, the standard was brought up to reconcile these differences. However, what they came up with may not be any better. Instead of one standard, they invented essentially 16 standards. You have all these different standards that consist of all the characters necessary to facilitate bilingual, usually English to another language, communication. It was an 8-bit encoding, and we know 2 to the 8 equals 256, minus 1 for the null byte. So we have 255, basically, characters to work with. And that wasn't enough for most languages. From the very start, there were exceptions. There were things that just couldn't be fit in. I mean, in German, I understand the capital Etset character is not widely used, but it was still something that couldn't be represented. And from the start, we have to curtail the expressiveness of languages. More troubling, though, than this is that it allowed for bilingual communication between English and another, but it didn't allow for bilingual communication between two, let's say, target languages. For example, the Ottoman Empire, up until 1928, used a Perso-Arabic script. And then it was replaced by an alphabet. So you could transcribe Ottoman Turkish using Arabic characters using Latin 6, in modern Turkish using Latin 5, but there was no way to have both in the same document. Imagine being a scholar at the time and trying to capture some of the history during a vital time in that empire, that country's history. It was impossible. But of course, the elephant in the room, Chinese. You cannot represent that in 8 bits. With over 100,000 characters, depending on who you ask, this is not enough. It's not even enough for 2 bytes. We're going to have to do something else. The problem was that this is in the late 80s. Remember, this is 87. The web is being built now. So we ran a very real risk of running into another famous piece of art. This is the Tower of Babel. The breakdown of all human communication. Can you imagine a web where we couldn't talk to one another? That was a very real prospect until Unicode was created. That was in 1991. And that's the backstory and framing for everything. So if you want to understand Unicode characters, this is the history. This is what it is. Unicode is complex. It's huge. It's over 1 million code points, which is numbering characters, assigning numbers to characters. You have a basic multilingual plane, which is 65,536, and you have 16 additional planes, so for this grand total of 1 million. Right now we're using about 10% of the total allocation, so we're going to be all right for a while. It supersedes all previous text encodings, so it is able to capture and represent all, ostensibly all human communication, which is not, it's not a small task. Unicode itself isn't a text encoding. It only assigns characters to code points. So if you want to encode text, you have your choice between one of several different encodings, UTF-8, 16, and 32, having their respective 8, 16, and 32-bit representations. This gets a bit confusing, but some definitions up front kind of help with this. So we say that a string is a collection of characters, okay? A character consists of one or more Unicode scalars, and characters are encoded into a sequence of bytes. So let's actually bring up some Swift code, because this is ostensibly a talk about Swift, or something. We have a string, the word cafe, with a baguette emoji. Not to be too stereotypical, but we can enumerate over the characters in it. In Swift 4, they changed back. It's gone back and forth a couple times. But now, a string is officially a collection of characters, and you can enumerate over those. And for the sake of understanding it in computer terms, a character is whatever you expect to disappear when you hit backspace. That's it. The term, another term used is extended grapheme cluster, which I think does more to confuse and confound people. Just if you ever wonder what a character is, hit the backspace key. And if you run the code from before, you get what you expect. You have the letters capital C, A, F, E with an accent acute, a space, and the baguette emoji. Of course, there are some complexities here too. Some characters consist of multiple Unicode scalars. So you can have E with an accent acute as a combination of E plus combining accent acute. But because French in earlier encodings had a character with E and the accent combined, that is also encoded. So you have denormalized and normalized forms. And it's actually impossible to figure out the length of a string until you go through each individual byte and do the Unicode calculation for how characters combine with one another. If you ever wondered why, annoyingly, you can't do this, you can't access arbitrary indices for characters in a string, that's why. It's just not, it's not the way that you can really reasonably think about a string. If you want a better understanding of what's going on underneath everything, you can do this all in Swift. If you enumerate over the UTF-8 bytes, the UTF-16 bytes, and the Unicode scalars, which are pretty much the same as a UTF-32 representation, Unicode fits well within 32 bits, so you can just represent the number that's assigned with this 32-bit integer. You can generate a table like this. So anytime that you want to know what is actually going on with your string, you can do that in code. You can see that, for instance, emoji, they have each character is assigned a single code point in Unicode, but it takes 4 UTF-8 characters to actually encode that because the number's so big. But for small characters that start way at the beginning, basically ASCII, you can do that in 1 UTF-8 byte. So let's keep on moving on, though, because I think we're falling behind. Let's talk about identifiers really quickly. So let's say you have a product that, among other things, has an identifier that is a string. The problem with this is that this API surface area is enormous. The moment you introduce a string into a type, you incorporate all the semantics of string manipulation, normalization, introspection, pretty much everything that we talked about. It's not only distracting, but it leads to potentially bad behavior. So a better approach would be to define a nested type, a nested identifier type that encapsulates the underlying string value. As of Swift 4.1, equatable and hashable conformants are automatically synthesized for you, so there's less overhead for creating a formal type around this. As currently implemented, though, there's a shortcoming, and that's that it's cumbersome. Nobody wants to type all of this, and we can't really expect them to either. When people have the choice between what's convenient and what's correct, we all know what they decide. So why not just make it convenient? I mean, the ultimate convenience of strings are string literals, which are that you can initialize a string based on a value that you can see in source code. We take this for granted with strings, but we can also give this behavior to custom types as well, like that. The way you implement this is that you extend a type and have it conform to the expressible by string literal protocol. That has a single requirement in and of itself, which is just a string initializer, initializing from a string literal value. And if you've created a simple type that just encapsulates a single string value itself, it's actually pretty simple. Now we get the convenience of strings with the safety of an encapsulated type. We can do something like this. Or, because Swift is really smart and can infer the type, we get basically the behavior we had before, but now it's not so bad. So if we start to type t.identifier and look at the methods that come up, basically the only thing that comes up is hashable, which is nice to have. We could rip that out if we don't need it. And you might take things a step further. You could make an identifier that's a generic type that allows you to use string or integer types. You can have a lot of fun with this. And really, a custom identifier type makes more sense than a bare string. If you think about other identifying information, like credit card numbers or barcodes or URLs, they all have string representations, but restrictions about what values are allowed, and maybe conventions about how they're presented. So for example, an initializer is a great place that you can do validation. This example should be throws instead of using fatal error, but this is a little bit easier to read. In this case, we have preconditions, some validations that say a string identifier can't be blank, it can't be too long, and in this particular case, it must be a food emoji. You can do that. Or if you wanted to normalize it, you might lowercase all incoming strings, which makes for maybe easier comparison that you don't have to go all the way through and see Unicode canonical equivalency. You can just compare bytes. So on the subject of identifiers, paths, URLs, let's talk about those. So URLs aren't strictly speaking strings, but strings comprise their components. RFC 3986 defines rules for the structures of URLs, what characters are allowed in which places. And of course, you all know that Foundation comes with some really great types to manage these. You have URL. You also have URL components, which is really nice because it allows you to access each of the individual components in URL in a nice way. If I were to take the French kit URL and add a fragment croissant, because again, stereotypes, we could then rip out the URL later Fragment's a kind of obscure one. That's when you click on an anchor tag in HTML, that's the thing that gets appended with the octothorpe, the number sign at the end. However, again, as I said, URLs, you can't have all characters in all places. And in fact, there are restrictions on characters basically above ASCII, if you think about that range. So if we wanted to, for example, link to a fragment like, again, croissant emoji, the URL that you get out at the end doesn't look like an emoji. It doesn't look like an emoji at all. It's just a bunch of hexadecimal sequences. What is this? This is called percent encoding or URI encoding. And any out-of-range characters, either because they don't fit in the normal characters that are allowed in a URL at all, or because they're just not allowed in a particular place, they're encoded with a percent sign plus 2 hexadecimal digits. Those digits are themselves the UTF-8 sequence of the character being represented. There you go. So if you ever wondered what that is when you work with a URL, there you go. Next up, let's talk about natural language text, or strings that contain text written for or by humans. Written language in its essential form, you might say. New in iOS 12, yay, and macOS Mojave, the natural language framework reorganizes and expands on the existing NLP APIs that you got from Foundation. And it also incorporates some machine learning internals. The functionality of Foundation's NS Linguistic Tagger, very thankfully, has been split into 3 separate APIs, and each of those APIs is big enough as it is, so good to be moving off from a jumbo API. Each one of those accomplishes a different essential task in natural language processing. So the first of which being tokenization, which is dividing up natural language text into paragraphs, sentences, and words. You can take a string. I mean, you might do this trivially. If you just were a functional programmer, let's say, and you just thought that maybe all paragraphs are just delimited by new lines, words by spaces, and sentences by periods, you could do this. You might even pat yourself on the back for how compact that is. I got bad news for you, though, because as soon as you encounter, let's say, Chinese text that was written on a Windows platform, that's not going to work. They don't use spaces to delimit words. They don't use the same period character, and Windows uses a different new line character sequence. You might say, but my app, it's only for, well, this is more true of people in America that only believe that America exists, but we all know there's no such thing as the English language. It's everything. There's only one universal language, and it just happens to have different parts of the languages that we're familiar with. So we have to be ready for everything, pretty much. So here's how you use NL Tokenizer. It's kind of boring to go through code, so I'm just going to skip that. You can check it out in the slides later. It works as you expect. You can also do tagging. So NL Tagger allows you to do part-of-speech tagging. So you have an example sentence like this. If you give it the lexical class tag scheme, it will give you the part-of-speech for each. So it'll say the is a determiner, quick is an adjective, brown is an adjective, et cetera, et cetera. You could alternatively use another tag scheme to get the lemma of words, so the uninflected version. The word jumped becomes jump, which can be useful. This class supports French and other languages as well, although the official list isn't actually published. So check it out. NL Tagger can also do named entity recognition, so that's another tag scheme you can do. If you have a sentence like Tim Cook is the CEO of Apple Inc., based in Cupertino, California, you could set up the code like this and have it recognize each of the names. So you get personal names, organization names, and place names, which can be really helpful if you want to extract information from natural language text. But one of the coolest features is that you can extend this yourself. You can create custom tagging models using CreateML, one of my favorite features in the latest SDK release. You can create your own training data, so you tag examples based on what you're interested in. And then when you go through and you create a new model, you assign it a tag scheme, and you try to parse, you tag a new string, you can identify, for example, the product names, Apple product names in a string, which is cool. Okay, really quick, just one last piece of natural language processing I want to talk about is transliteration, which is more or less just transforming text into an equivalent representation. One example is just what happened there with that fancy slide transition, which is stripping characters of their diacritics, accents, umlauts, that kind of thing. So if we had a string with lots of dangly bits on top, you could apply the string transform strip diacritics, and you could get the bare string transliteration from it. This is a foundation API built right into string. However, there are a bunch of different transforms that are provided by the Unicode Common Language. It's the International Components of Unicode functionality. So you could, for example, do a transform to convert Korean Hangul into Latin. Although it takes maybe 30 minutes to learn Korean, maybe you don't have 30 minutes or you're too lazy, this would allow you to get a fighting chance at maybe pronouncing an unknown string using a character set that you're familiar with. I've used this in the past to create full text indexes on local core data stores. If you transliterate all text into Latin, which seems to be the easiest one because it's the one that most languages have transliterations for, you can get a rough approximation of multilingual search. It's pretty cool. So similar to natural language processing, we have number 5, structured data. Text often contains things like dates, locations, phone numbers. If you use another foundation API like NS Data Detector, you can extract this information, structured information, and get structured information out. Dates, address components, phone numbers, URLs, flight information. So we have a string, which gives you maybe the start time of French kit, where it is, and a URL to access. If you pass that into an NS Data Detector and you enumerate all of the matches in that string, you will get the information that you expect. And even it'll be time zone sensitive, which is neat if you give that information in the string. It's very neat. However, structured data is great until you have to cross API boundaries. If it's binary data, especially, that can be problematic because some systems don't really know how to deal with binary in a safe way. So number 6, it's a way to, let's say, protect your data. What we call ASCII armor. This is called base 64 encoding, and based on our understanding of encodings from before, it's just assigning 64 characters, 64 numbers to characters that are widely represented across different text encodings and just basically characters that we understand. So we get A through Z, both lowercase and uppercase, 0 through 9, and we got 2 more, so why not plus and minus? By doing this, we can code, this is the UTF-8 representation, binary representation of the string above, encoded as base 64. And if we were worried about binary data not making it across an API boundary, then base 64 encoding saves that. It's not very efficient, though. You'll notice that the bottom version is a lot larger. That's because 64 bits is less than the 256 for a normal byte. So it's, what, 5 divided by 8? It's that percentage efficient. If you want to do this yourself, again, Foundation has an API to do this for you. You can do the base 64 encoded string method on top of a piece of data, or you can initialize a string based on data using the data that you convert back from base 64. So you do a round trip right here, works as you expected. What are some use cases, though? So mail, anytime that you receive a message with an attachment, a multi-part message, those can be encoded using base 64. Or let's say you are a web developer or you're developing something with a web view in an app. You could base 64 encode a font or an image, and that would allow you to reduce the number of requests you make to a server. Or if you're just worried about getting paths to resolve right, this is a way to bulletproof your logic around all of that. Or let's say you were for some reason averse to asset catalogs or resources directory in a playground. You could, or just want to do it in a single file. You could have a ping image, for example here, encoded right into your source code. So you can initialize right from a string. All right, so last up, we're going to finish off with a brief talk about typography. So far, we've been, something to keep in mind is that we're talking about characters, which are different than glyphs, their representation. Unicode characters are abstract. There's actually no strict adherence to how something is shaped. And we know that, fundamentally. If we look at Latin capital letter A, we know that typesetting software can render it differently based on the font or the context. It can look very, very different depending on the font. In some written languages like Arabic, the glyph of the character depends on its position in the word. So for example, you have initial, if it's in the beginning of the word, you have medial, final, and then isolated forms of a letter. I mean, we have this in English as well, and I think French, if you have the letters F, F, and I, the typesetting software might combine those into a single unified glyph that's easier to read. That's called a ligature. But by far, the most interesting use case of glyph shaping comes from emoji. So instead of having one code point for each country, which is bound to change over time, instead there are 26 regional indicators. Each one represents a character from the English alphabet A through Z, and those are regional indicators. So if we take regional indicator F plus R, you get the French flag because the ISO 3166 code for France is FR. You also get some cool ones like this. Different like non-country flags work differently. So white flag plus this zero width joiner character plus rainbow, you get the pride flag. Or new in iOS 12, you can try this out for yourself, black flag plus zero width joiner plus skull and crossbones, pirate flag, Jolly Roger. This is problematic though, I think. So on Apple platforms, if you do cat face plus zero width joiner plus laptop, you get cat face plus laptop. However, on Microsoft platforms, you get hacker cat. I'm not sure how many people in the room can try that out, but just ask your Windows friends. Between this and the looming threat of a frowning pile of poo emoji actually making it into the standard, I think this is a disaster. 10 years ago, I don't think we would have predicted that the iPhone would usher in a new ideographic paradigm for language by way of emoji. The Unicode Consortium went from solving problems fundamentally about human expression to being the clearinghouse for all human expression. Looking forward, I have to conclude, unfortunately, that history repeats itself now. Rome is burning. Human communication is doomed. We're done. On that note, thank you.
Thank you. Thank you very much.
Sure. Oh, I got a quick plug if we're not going to transfer off slides.
Oh, nice.
So I write a book series called Flight School. It's a lot of fun. These are new covers. We have one on codable, we have one on numbers, and if you liked what I was talking about with strings, you'll look forward to the next book coming out this fall. You can follow us on flight.school. Thanks.
Yeah. Okay. Yeah, can you first tell us a bit more about Flight School? Because it's kind of your new activity, and I think it's really interesting to see what you're up to.
Yeah, so like I mentioned, I dropped out of the computer science program when I was in school, and I sort of feel like I missed out on a lot of that. And there's a lot of maybe imposter syndrome that comes with this, especially as we learn about cool things like networking theory or databases. You always feel like you're sort of a step behind. So what I wanted to do was create a book series that was all of the CS education I wish I had had at the time, plus some information that you get only over maybe a decade or two of a career in software development. Also, there's an aviation theme there too. I love flight.
You mean you suffer from the imposter syndrome?
I mean, yeah, who doesn't, right? I mean,
yeah, it's good to know. Good to know. So it seems like building something like Unicode is a huge work. Like, do you know how it works and like who decides?
So there's the Unicode Consortium, which right now it seems like it's a cabal of the tech companies you expect: Microsoft, Apple, Google, everybody that has a horse in the game in the race for representing language. And it's like any other standardizing process. You don't want to see the sausage being made. It's a messy process of politics and academics. It's a lot of fun though. If you ever have the chance to look into like any of those discussions, it's fascinating.
Mm-hmm. Yeah, but I guess there are lots of cultural topics, and so there's no countries involved or things like that.
Oh, country. So yeah, actually, that's a great point. National governments have representations if they want to make sure that their native language, their native script, has first-class support. So you see a lot of countries doing that. And different countries objecting to, in the initial formation of emoji, it's wonderful. I was just looking over transcripts of how they named the initial emoji because, pictorial symbols from Japanese cell phone carriers, there are going to be some differences in culture between that and, the rest of the world. And how they reconciled that is amazing.
About NL Tagger, do you see? I was wondering why Apple introduced that at the time, and do you see other kind of places where we can actually use that? Because it seems there are plenty of things that could be done, but like as always, hard to see like up to which level it's accurate, and can we really use that in prod for like a real life application?
Absolutely. So, I mean, the first step in taking a piece of natural language text is to understand it. And, you know, if you wanted to, as a first pass, let's say you wanted to, I mean, Siri probably does this to some extent. If you say something like, hey, Siri, do this for me, it's going to discard pretty much everything except nouns and verbs. Mm-hmm. So if you wanted to create, you know, kind of a dumb artificial intelligence layer, just prototype something, this is a great opportunity. Or if you want to index on the most interesting words, yeah, you just maybe get the personal names, the place names, and nouns.
Interesting.
I have a question which is a bit lightweight, but it's related to what you showed in the last slide about Rome. It was just burning. Mm-hmm. Do you think it's actually it can happen? I mean, I guess today it's so easy to send an image or a complex character over the net that changed things forever, I'd say. Do you think it's actually kind of something that can really happen, that those characters make into the press, of everyday press, like newspapers and...
Oh, absolutely. I mean, like, you can't walk through a mall without seeing, emoji pillows on sale. Like, people love that stuff. People love emoji. It's it's the universal, like, that's the universal language. But consider the recent controversy around the change of the pistol emoji. Mm-hmm. So it went from being a gun to a water pistol, which that's changing the meaning retroactively of every use of that previously.
Oh, interesting.
Yes. So usually languages would just change over time.
It's basically 1984, right?
I mean, it has some parallels, I think. And I think if we're going to be, vigilant against the decay of language, or just understanding how these decisions impact our daily lives, we might look at this and say it's a silly example, but I mean, these things can escalate really quickly.
Yeah. I can start with that.
Super interesting.
Thank you very much for your talk.
Absolutely.
Thank you,
for having
Matt.
the opportunity. Thanks.